Okay. So we are going to be talking about intermolecular forces and electronegativity. So just to start off with a couple definitions, IMF stands for intermolecular forces. We're going to use that acronym all the time. But they are forces between bulk particles. Bulk meaning like Costco, right? You buy things in bulk, so there's a lot of them, not just one thing by itself. And then along with that, we have something called polarity, which is the separation of charge. And we get a lot of things like dipole movements with that, positive and negatively charged things. And remember, with your arrow and electronegativity differences, you represent dipoles with like that little weird squiggly with a minus and a little weird squiggly with a plus. And the arrow always points towards the one that is more negative. Where you can find electronegativity differences, on the back of your pink periodic table, we glued on a sheet a periodic table that has little values underneath them. And they have those electronegativity differences. And so in order to find the electronegativity of something, let's say, for example, carbon, I would find that on my white periodic table with the electronegativity differences. It has a value of 2.4. All right, so that's how you find it. And so just to kind of talk a little bit about the differences between electronegativities and what that means, we have a couple different examples. Remember our covalent bonds and our ionic bonds and how we find that on the pink periodic table, right? So if you're talking about ionics, you have something that is positively charged and something that is negatively charged. On this periodic table right here, it's everything that is pink, right? We didn't color it in. Those are all the positive ones. Covalent, that's okay. So in order to find out if something is ionic or covalent, just looking at the pink periodic table that we have, we're going to start with the different types that we have. So if you remember, finding an ionic bond means looking at your pink periodic table, finding the pink values over here, they are positively charged. And what they do is they will bond together with one of these green elements over here, and those are the ones that are non-metals, okay? Non-metals. In this D block here, those are considered metals, but we're just going to focus on these ones over here matched up with our green ones over on the other side. So that's an ionic bond. What happened? Okay, so in order to find whether or not you have an ionic or a covalent bond, just looking at your pink periodic table, and we're going to connect that to those electronegativities. So you got your pink periodic table. On this one, everything that is, for an ionic bond, you need to have one of these metals right here. They're positively charged, and they are written in pink on our periodic table. They are going to be bonded with one of these green guys over here, all right? So these green guys are the non-metals, and they have a negative charge to them. Another thing you should notice about periodic trends, if you remember the PASTA activity, is low electronegativity values are commonly associated with positively charged metals. Those are those pink ones right here. Higher electronegativities are usually associated with the green nonmetals or the things that are more negative. And that will become really important when we start writing out our dipole thing, because as you can see, the things that are more negative have that arrow pointing towards them. And so that's one of the things that we're going to be keeping in mind as we model our electronegativity differences. All right, so moving on then to covalent here. Looking at the pink periodic table, covalent bonds are a mix between a nonmetal and another nonmetal. So for example, on here, we've got our green nonmetals that we have listed. It's a bond between two of those things, all right, two or more. And so electronegativity differences are really, really close together when you have two nonmetals. So their differences in the dipole-dipole movement will be slightly different. Usually a smaller difference. And then, so we'll have, there's two different differences, right? We've got things that are nonpolar. And what nonpolar means is when you have electrons that are shared mostly equally. Remember, we have those electrons that exist in the cloud, or they're in a sea if you have a metallic bond. These ones are shared very equally, and you'll have a value of electronegativity value difference of 0 to 0.4. The next one that we have is a polar covalent bond. These are when electrons are shared unequally, resulting in a bond that is partially charged. All right. And then those values usually range between 0.41 and 1.7 on our electronegativity differences. Now that partially charged piece there, that's what that dipole separation is related to. And that's how we determine whether or not something is more electronegative than the other. And it helps us model those polar bonds. Perfect. So we're just going to show you a couple different examples of these intermolecular forces. Our first example will be between the two elements magnesium and oxygen. So when you look at your white electronegativity difference periodic table that you have glued to the back of the pink one, you'll find that magnesium has a value of 1.2. You'll find that oxygen has a value of 3.5. So what we need to do is we need to find the change in electronegativity. So we're going to have to subtract these two things. So triangle in science language means change, En being electronegativity. Now remember, this is the absolute value. You can never have a negative electronegativity value. Okay, so keep that in mind. If it's negative, you might want to switch around. So when you subtract those two things, you're going to get a value of 2.3. Looking at that chart there, if we said that a value of 1.7 or higher is ionic, then that means that we have an ionic bond. You can also double check your work, right? You 100% should do that every single time. Find magnesium here, find oxygen here. This one's pink, this one's green, ionic. It's a good way to check yourself. It's not always correct though, so keep that in mind. All right. So here we are, those Lewis dot structures that we have been working on, and we're going to show direction of transfer. Remember, we use arrows for ionic, circles for covalent. That's what it would look like if you drew it out. All right, so there's one example. Our second example, we are going to do carbon and chlorine. Okay, so carbon has an electronegativity value of 2.5. Chlorine is 3.0. All right, so when you find the change in electronegativity difference, make sure you once again do the absolute value of that. No negatives, no negatives. The difference will be 0.5. All right, look that up on your little chart that we gave you. 0.5 would fall under that polar covalent category there. So that's how we know. Another good way to check, make sure those are two nonmetals. When you look at your pink periodic table, they should be. And then another thing you should note that these are not diatoms. They have definitely a good difference between them, so that automatically assumes that we do not have a non-polar covalent, that there is some partial charge to this piece here. So there's the Lewis dot structure with that. And as we know, polar covalent bonds are shared unequally, and that's what those circles are representing. Those dots are not the same, and they are spread out in unequal ways. Take a look at where we're putting those dipoles at. The negatively charged one is with chlorine because it has a higher electronegativity value. The positively charged dipole is with carbon because it has a lower electronegativity value. So when drawing that arrow, the arrowhead points towards chlorine because it has the negative dipole movement. Awesome. All right. All right, so we have one more example for you. We are going to take a look at carbon and hydrogen together. So when you look at your electronegativity table, carbon has a value of 2.5, hydrogen has a value of 2.1. When you take the change in electronegativity, making sure everything stays positive, when you subtract those two values out, you get 0.4. Taking a look at our chart, we see that 0.4 indicates that we have a non-polar covalent bond. All right, so if it were 0.41, it would be a little different, but it's not. And so what that means then is we have electrons that are shared mostly equally. And so, you know, you get a lot of these when you have just that really small difference between electronegativity. You'll also see a lot of nonpolar covalent bonds being diatoms, which means you have two of the same element. And so taking a look at the circles and how these electrons are shared rather equally, even though it's not perfect, obviously, but that electronegativity value shows us that those are going to be equal, and that's how we know we have a nonpolar bond. All right, so we have another example for you for a nonpolar covalent bond that shows a diatomic bond. So we're going to do it for oxygen and oxygen. So, you know, when you subtract 3.5 and 3.5, which are the electronegativity values, you're going to get 0. Not shocking. So that automatically tells us it's a nonpolar bond. And those electrons then will be shared equally, and you get a structure that looks much like the one shown below, diatomic. So another way that we need to figure out whether or not something is polar or nonpolar covalent is to check out what these molecule structures look like and finding out their symmetry versus non-symmetry. So starts with the molecule structure. So for example, I have two yes and no symmetries. You take a look at them. In the center is where you need to start looking for if something is symmetrical or asymmetrical. So as you can see, the central atom there is that little white one, and each of the branches that come off of that atom are a different molecule or a different atom within itself. And if you look, everything left and right, up and down from that central atom is the same. So what that means then is we have a nonpolar covalent bond. All right, symmetry means nonpolar covalent. If you need to remember what symmetry means, think of a butterfly, right? Same on both sides. And then on the opposite end, when you look at the central atom of the second molecule, you'll see at the top there, there's like a completely different looking atom. What that tells us then is that this structure is asymmetrical, and asymmetry means polar covalent because we're going to have that partial charge, right? We're going to have to find those electronegativity differences that are like pulling on each side of those molecules. Okay, so we're going to take a look at 8 examples here, and we're going to start in the top left. So you see there, you've got that central atom. It's got a double bond, but it has the same atoms on both sides of that. When you still take the symmetry of it, you're going to have something that is symmetrical. Even though there is a double bond, it's the same atom on each side, and tops and bottoms look the same as well. So then we're going to have a non-polar covalent bond. The second one there has another, it has 2 of the same elements on the tops and to the right, and a different one down below. That automatically tells us it's asymmetrical, which means it's polar. Number 3 is like a chain, think similar to just a bunch of like repeating carbons possibly. If we take that to the top and to the bottom from the middle one, you're going to see some symmetry. Symmetry means nonpolar. Number 4, if we take a look, you'll see those lone pairs that are on top of that oxygen, and you'll see 2 different atoms pulling from that central there. That's asymmetrical within itself. Those lone pairs have a lot of pull and dipole movements, so we will have a polar bond. Number 4 up there, you'll see it's got 4 of the same, and then there's that X up there with that little red dot. That automatically pulls away and it makes it asymmetrical, meaning we have a polar bond. Taking a look at this next one here, everything from the central atom is the exact same. There's no lone pairs or anything like that. This one is symmetrical, so it is nonpolar. This one here is pulling, and it's kind of one of those tricky ones. You got to watch out for this one. It looks like it should be symmetrical and perfect and everything like that, but what we're not having is this area that is being circled right up here. Those are the lone pairs that are missing from that. You know, carbon needs to have 8 in order to be happy. Lone pairs, when you see those, are oftentimes associated with, and will take away symmetry, especially if there's only one pair. So that would then make it asymmetrical, meaning a polar bond. Last and not least, you have a red circle and a smaller black circle. Those are not the same. They are not diatomic. They are different elements making them polar. So what we would have done in order to assess this, and what we're going to have you do, is make some models of these and interpret them. If you remember doing that as one of our standards. What? Oh yeah, I'm going to start that up. We are going to give you a couple examples of some models of these particular IMFs. So making sure that you can interpret polarity from a particle model. So take a look at these 3 examples that we have here. Pause the video and try to identify them yourself. Are they polar covalent? Are they non-polar covalent? Are they ionic? What are they? All right, so pause the video and we'll go over them. Okay, pause. We're done with that. All right, welcome back. So if you take a look at that first one here, you're looking at that central carbon atom, probably. And up above there is a benzene ring. That automatically tells you right away that this is an asymmetrical molecule, meaning that we're going to have a polar covalent bond. All right, if we had a benzene ring down below, might be a little bit of a different story. All right, then taking a look at this next one, if you cut it left to right, up and down, you're going to be able to have everything on the same on each side. So that means everything is symmetrical, giving us a non-polar covalent bond. All right, last and not least, automatically you should see those charges and be like, oh yeah, positive and a negative. That means something to me. And you already noticed too that Na has transferred its electron over to chlorine. Taking a look at those things, you know a positively charged atom is metal, negative is non-metal, making this an ionic bond. And also you'll have the electronegativity differences that will support that. So when you look and find sodium and chlorine, taking the difference, it'll be 1.7 or higher.